Hello guys, this is CodeNCode and this is the 9th lecture of this number theory series, and in this lecture we are going to study about modular arithmetic. So let's start the lecture. So in this lecture we will be studying different techniques and formulas related to modular arithmetic. So the first thing that we start with in modular arithmetic is modular congruences. So A and B are said to be congruent to each other under modulo n if they have the same remainder when divided by n. So this is represented as this: A is congruent to B. A congruent sign is made up of 3 dashes. So A is congruent to B under modulo n. This is how we represent two congruent integers. For example, 13 and 14 are equivalent or are congruent to each other under modulo 7 because they leave equal remainder when divided by 7. 16 modulo 7 is 6, and same is for 41 modulo 7. So two numbers are congruent to each other under modulo n. N can be any integer if they leave same remainder when divided by that number. So we have studied, we have seen what are congruences. So what are uses of congruences? What are the scenarios we can use congruences? So as explained earlier, congruences are used in modular arithmetic. I mean almost everywhere. For example, look at this equation. We wanted to calculate 13 plus 35 plus 5 modulo 7, which would be 53 modulo 7, which is 4. Now as we know that 41 is equivalent or congruent to 13, can I replace 13 with 41? The answer is, let's check. I've replaced 13 with 41 and rest are same. Their sum is now 81, but still 81 modulo 7 comes out to be 4. So this is one of the use cases of congruences. When two integers are congruent to each other and you are working under the same number, here we see we were working under modulo 7 and these are congruent to each other under modulo 7. Remember, if you change the integer here, they may not be congruent to each other. Now since we were working under modulo 7 and under modulo 7 13 is congruent to 41, we can replace 13 with 41 and the result won't change. Let's see for multiplication as well. If you multiply 13 with 4, and we have to calculate 13 into 4 modulo 7, so 13 into 4 would be 52, and 52 modulo 7 comes out to be 3. After replacing 13 with 41, which was equivalent or congruent to 13, we get the same result again. Even though the intermediate result may change, but the final result is still the same. Now let's see why this happens. While we were calculating this, there are two ways you can calculate it. First, compute these things completely like we have done here. We have first calculated the sum of all these integers, and then which comes out to be 53, and then we have taken modulo with that number, modulo of that sum with integer 7, and the result is 4. The other way is you can initially take modulo of individual number and then add it, and then you see whether you have to take modulo or not. So what I want to say is that we can do this. We can take 13 and apply modulo on 13 with 7, and then 35 and 5 individually, and then add them. We are applying a modulo operator before adding them, you see. So 13 modulo 7 would be 6, 35 modulo 7 would be 0, and 5 modulo 7 would be 5. So we have applied modulo operator even before adding. There are two ways: either just apply the operators and then apply modulo as we have done in first equation, or apply modulo operator before addition and then add them, the result comes out to be 11, and then see if you have to take modulo again. Since we have to take, because this is not remainder, this is above 7, so the remainder must be different, so we have to divide it again or take the modulo. So 11 modulo 7 is 4. Now you see, if I replace 13 with 41, this equation that we have get would not change, because 35 and 5 would still be 0 and 5. But if I replace 13 with 41, we know these two are congruent, which means they would leave same remainder. So even if I replace 13 with 41, if I apply a modulo operator before adding, I am still bound to get 6. I will still be getting 6 instead of any other number. So if the equation doesn't change, if this equation doesn't change, the result won't change. And the equation won't change because they both leave the same remainder when divided by 7. And that is why even if I write 13 or 41 or any other number which is congruent to 13 modulo 7, the result won't change. That is why when two integers are congruent, you can replace one with another and the result won't change. This applies to operators addition, subtraction and multiplication as well, but not with division. To work with division, we have something called modulo multiplicative inverse. You might have heard it somewhere during in some competitive programming contests. Modulo multiplicative inverse are there to work with division operators, because we can replace one with another if two integers are congruent to each other in addition, subtraction and multiplication, but we can't do the same in division operator. For that we would study about modulo multiplicative inverse. Now one important property of congruency is that if a and b are congruent to each other under modulo n, then their difference is congruent to 0 modulo n. Their difference is congruent to 0, which means they leave 0 remainder when divided by n, and they leave 0 remainder indicates that a minus b or b minus a, that is their difference, is actually divisible by n. You know, if a number is divisible by another number completely, then number 1 is actually divisible by number 2. That is the only way we get remainder 0. Now if a and b are congruent to each other, then their difference a minus b or b minus a would be equal to or would be congruent to 0 modulo n, and that is their difference is divisible by n. So let's prove this fact. Now see, I've written a as n times k1 plus r and b as n times k2 plus r. If you are following this series, in the previous lecture I have told you and we have studied about Euclidean algorithm. While we were studying Euclidean algorithm, we have talked about Euclid division lemma, and this is just Euclid division lemma. I've applied Euclid division lemma and written a in terms of n as a is equals to n times k1 plus r, b is equals to n times k2 plus r. Now you see the remainder are kept same, both are having remainder same, because a and b are congruent to each other. That is why the remainder would be same. Now if we apply the subtraction operator, a minus b would be nk1 plus r minus nk2 minus r would cancel r, and then we would be left with n times k1 minus k2. Now this equation proves that a minus b is divisible by n, because k1 and k2 are integers and their difference would also be an integer. And if I take n here, this side, left side of the equation, then the left side would be a minus b divided by n is equals to k1 minus k2. Since the right hand side is an integer, hence n completely and evenly divides a minus b. That is a minus b, that is the difference of two numbers, is divisible by n, and that is the proof. So if two integers are congruent to each other under some modulo n, then their difference would be divisible by that number. Now to take an example, we knew 13 and 41 were congruent to each other. Then you can see their difference, 13 minus 41 comes out to be minus 28, and 41 minus 13 comes out to be 28, and we know both of them are divisible by 7. This was just an example. We have already proven this fact. Now we know if a minus b is divisible by n, then we can write a minus b is equals to n times k, where k is some integer, can be positive or negative, or even can be 0. Now if you manipulate the equation, you can write it as a is equals to n times k plus b. This is an important equation. If you combine the properties of this equation and this, or observation of these two equations, it comes out to be very interesting observation. See, you had some integer b and you added k times n into b, and then transformed b into a after adding kth multiple of n. Now even though you transformed b into a after adding kth multiple of n, even though their remainder doesn't change. And how we can tell that? The remainder is same because by this equation their remainder is same because they are congruent to each other. So initially whatever was the remainder of b, still after adding n k times, its remainder doesn't change. So what it tells you is that if you have a number b, you can add n as many times as you want, add or subtract, because k can be negative as well. So add or subtract n as many times as you want, its remainder would still be same under modulo n. To make this fact a little more clear, let's look at this analog clock. The clock is actually modulo 12. The reason is that because every 12 hour, the what we call is hour hand is at the same position. What I want to say is that if hour hand is currently at 6, then after 12 hours it would be again pointing at 6. So suppose it was 6 a.m., then after 12 hours it would be 6 p.m. That is, the hour hand would be coming back to it again after 12 hours. That is, each number repeats itself after 12. So there is a repetition after 12. So the system is actually modulo 12. So 12 can be considered as 0, and then 1, 2, 3, 4, 5, 6, dash, 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 11, and then again 0. Now you see, if you initially the hour hand was on 6, if I ask you to what would be the position of hour hand after exactly 12 hours, of course your answer would be the position of hour hand would again be on 6. Okay, what would be the position of hour hand after 24 hours? That is 2 times of 12, because we are talking about modulo 12. So after in 6, if you add 2 times of 12, that is 24, it would become 30, and 30 modulo 12 is still 6. That is, even after 24 hours, after exactly 24 hours, the hour hand would be again pointing at 6. That is, if you add again and again n working under modulo n, then its remainder doesn't change. Initial remainder was 6. If I add 6 into 6, if I add 12, the number would become 18, but still 18 modulo 12 is 6 again. If I add 24, which is second multiple of 12, even though the result becomes 30, and 30 modulo 12 comes out to be 6 again. So you can add any multiple of n, the remainder of a number doesn't change, even though we have transformed b into a after adding k multiples of n, even though their remainder doesn't change. So to represent this equation, we can since a and b are congruent to each other, and we see if a and b are congruent to each other, you can write a as n times k plus b, or b as n times k plus a. So to represent this fact, take an example like this. We know 13 and 41 are congruent to each other. So I can write 13 as 7 times minus 4 plus 41. It would result into 13, or 41 I can write it as 7 times 4 plus 13. So if two numbers are congruent to each other, you can write it as a is equals to n times k plus b, where n is the number under which we are working, or n is the number with which we are taking modulo. So this is an important equation, just remember that. If a and b are congruent, they can be written as in this form: a is equals to nk plus b. Now let's continue. This is very important because in competitive programming there are many situations when you have to calculate result suppose c as a into b modulo some integer n. So this states that multiplication under modulo, this states that if we have three integers a into b is equals to c, then a mod n into b mod n is congruent to c mod n. Basically, a modulo n into b modulo n is congruent to c modulo n. To take an example to understand it better, let's take 13 and 9 as an example. So 13 is equivalent to 3 mod 5, 9 is equivalent to or is congruent to 4 mod 5. Now we have to calculate 13 into 9 modulo 5. Now 13 into 9 modulo 5 can be calculated as 13 mod 5 into 9 mod 5. By this fact we know that 13 mod 5 into 9 mod 5 is equivalent to 117 mod 5, because 117 is multiplication of these two numbers. So 13 mod 5 is 3 and 9 mod 5 is 4 and 117 mod 5 is 2 and 3 and 4 are 12, which are equivalent to each other. So we see, okay, if there are three integers a into b is equals to c, then here you can see it is an equation because we are using equal sign, and here it is a congruency because we are using congruency sign. So if you have an equation of the form of a into b is equals to c, then it comes out to be a congruency of a mod n into b mod n is congruent to c mod n, which is true if we look at this equation, but we have to prove it formally. If this holds, then calculating result becomes easy in competitive programming, because suppose you have to calculate result a into b modulo some integer n, suppose 10 to the power 9 plus 7 or something like that. What happens is that when you are calculating modulo, suppose a and b are long int. So the range of long int is roughly 10 to the power 19. Suppose a and b are 10 to the power 10 themselves. If you think, okay, let's multiply them first and then calculate modulo, what would happen is 10 raised to power 10 multiplied with 10 raised to power 10 would result into 10 raised to power 20. But 10 raised to power 20 is well above the limit of a long int integer. Yes, you can use big integer, but when you are working with C++ and you are not using boost library, then this would result into an overflow of long int, and hence all you would be getting is a garbage value. That would not be the actual result. So even if you calculate a into b modulo that 10 to the power 9 plus 7, and if you return the result, that would be wrong. So to work around that condition, what you can do is you can use this congruency, which states that a into b is equals to c. If you have that equation, then instead of calculating a into b and then modulo some number, instead of calculating that, what you can do is that you can first take modulo of first number, which was initially it would have been 10 to the power 10. If you take modulo of 10 to the power 9 plus 7, or suppose 10 to the power 9, it would be less than 10 to the power 9. Same goes for the second number. So a mod n and b mod n would be less than 10 to the power 9. If you multiply them, that would become 10 to the power 18, and 10 to the power 18 is inside the limit of long integer, so it would not result into overflow. And then finally take modulo to give the final result. So if we not had this formula, we have to go through this, and then we were forced to use in C++ the boost library, or in Java you can use big integer. But since we know that if a into b modulo c now can be calculated using this formula, then we can work around that overflow condition. To prove this fact, let's go back to Euclid division lemma. Now a into b is equals to c. Let's a be n times k1 plus r1, b be n times k2 plus r2, c be n times k3 plus r3. And now what we have to prove is that r1 into r2 is congruent to r3, where r1 is remainder of a when divided with n, and same goes for r2 and r3. Now we have seen that if two integers are congruent to each other, their difference is multiple of n. So we will use that fact to prove this equation. Now a1 a into b is equals to c can be I have replaced a, b, c with their corresponding values, and then I have expanded this. This would come out to be n times k1 k2 plus n k1 r2 plus dash 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 dash. You can see. And then since we have to prove that r3 minus r1 into r2 are multiple of n, since we know that if two integers are if two integers are congruent to each other, their difference is multiple of n. If we are able to prove that r3 minus r1 r2 are multiple of n, then that would conclude that r1 into r2 are congruent to r3. To use that fact, what we would do, we are having r1 r2, we would take them to the right hand side and then take this n times k3 to the left hand side. Then you'd see that all these terms contain something that is common, that is n. So we would take n common out, and then inside we would be having these. It doesn't matter what is this, I mean you can write it yourself. So what it indicates is that r3 minus r1 r2 are multiple of n, or that is they are divisible by n, because all the terms that are inside are integer, and their multiplication and addition and subtraction would result again into an integer. So r3 minus r1 r2, if I send this n on the right hand side, would become r3 minus r1 r2 divided by n. And since left hand side is an integer, then right hand side must be completely divisible, or r3 minus r1 r2 must be completely divisible by n, and hence r3 minus r1 r2 are completely divisible by n, which proves that r1 r2 is congruent to r3, and hence we have proven this fact. Since this holds, now we are able to use this formula and we can work around that integer overflow condition. So what it indicates, that if you need to calculate a into b, all you can do is a mod n into b mod n and then whole mod n. Same goes for addition, same goes for subtraction. You can prove for subtraction and addition by yourself. Now let's continue. Yeah, it is important to go for some problems after learning theories, because this is a better way to understand theories. Now first of all, we have to find the last digit of multiplication, the result of this multiplication. Now to calculate the last digit, if you are given an integer, you are working in a competitive programming, the first question comes and you are given an integer, you have to find the last digit. How do you do that? Of course, you take the integer and then find the modulo of that number with 10. The number was like 2573. You take modulo 10 and the last digit would come out to be 3, right? That is what we are going to do here. What we would do is we would do a into b modulo 10. That would be our result. But we know to calculate a into b into modulo 10, we can do a mod 10 into b mod 10 and then take multiply these and then take modulo again. So a mod 10 would be 3, b mod 10 would be 8. Now their multiplication would come out to be 24, and then we would take again modulo, which would come out to be 4. So multiplication of these two numbers result into the last digit of 4. So the last digit would be 4. Now let's continue. We have to find the sum and then modulo 2. Basically this expression modulo 2, what would be the result? We know that there are two ways. Either I can replace the number with their modulo of 2, either I can apply modulo operator before addition, or I can add them and then apply modulo operator. So let's do other way around. Just apply modulo operator before. So 142 would result into 0 modulo 2. 453 would result into 1 modulo 2, because this is even number would result into 0, odd number would result into 1. So same goes for this, because even, so 0 1 1, because the next two numbers are odd, and 0 1. The overall result would be 4 mod 2, which is 0. So instead of adding these completely and then taking the modulo, what we can do, we can apply modulo operator before doing that, and then after that we can take, if we can see if we need to apply the modulo operator again. Since this is above 4, this is greater than 4, that then we have to apply the modulo operator again. So the result comes out to be 0. You can add them and you would find that, yep, the result would be 0.